News of the Chinese Long March 5 rocket burning up on re-entry has made waves through the world, in some cases quite literally, as the debris from the rocket burned up over Saudi Arabia and splashed down in the Indian Ocean near the Maldives. And while it made a lot of people very nervous to know that a 22-ton rocket was gonna fall out of the sky, this sort of thing happens all the time. Boosters, dead satellites, and sometimes even old space stations get dropped out of the sky fairly often. While the litter may seem inconsiderate, this is probably far safer than the alternative, leaving junk in orbit. Just last month, a hole was found in a robotic arm on the International Space Station, punctured clean through by a fast-moving piece of shrapnel. The accumulation of space junk poses a huge risk to all human operations in space, especially if we cross the threshold into the chain reaction of exponentially growing collisions known as the Kessler Syndrome. The launch of Sputnik in 1957 kicked off the space race, and the number of satellites in space has grown ever since, and in recent years it's really taken off like a rocket. There are more than 3,300 operational satellites buzzing around up there. But they are not alone. They orbit in the midst of a giant cloud of debris. Rocket boosters, protective shields, old broken satellites and more. Around 10,000 objects that are large enough to be tracked by radar. They are uncontrolled and they are moving very, very fast. The quickest low-altitude orbits circle the Earth 16 times a day. A collision with one of these means instant obliteration into countless shards. And speaking of shards, there may be over 100 million pieces of debris so small that they can't be tracked. And while a loose screw or a paint chip may not be all that scary on Earth, at orbital speeds of 7 kilometers per second, they can carry as much energy as a cannonball. Right now, there are probably over 3 million kilograms of space junk, vastly outweighing our operational satellites and nearby natural meteoroids combined, forming a giant space tornado of death above our heads. The main thing protecting satellites from space junk is space itself. Space is, as the name implies, spacious, and so collisions are relatively rare, or at least for the moment they're rare. But as the number of satellites increases, the risk of collisions also increases. And collisions produce more space junk that produces more collisions. This sort of collision cascade is known as the Kessler Syndrome, after Donald Kessler, who pointed out the danger in 1978. The movie Gravity depicted this domino chain of destruction as unfolding over minutes to hours. Now, that's not how it would actually play out. In fact, the Kessler Syndrome is already playing out, albeit a lot more slowly, but it may soon speed up. To understand the risk we face, let's think a bit about exponential processes. The Kessler Syndrome is due to what we call a positive feedback cycle. That's any process whose outcome tends to increase the rate of the process, leading to exponential increase. The more space junk we have, the more space junk we make. But a positive feedback process can be prevented from entering that exponential mode if it's suppressed in some way. In the case of satellite collisions, exponential increase is inevitable unless the debris is removed from orbit or the risk of collision is mitigated. And that needs to happen faster and better than the rate that space junk is made. Let's talk about the mitigation first. Large pieces of space junk can be tracked using ground-based radar and more precise optical and LiDAR methods. And their future trajectories can be calculated to predict possible future collisions. A functional satellite in harm's way can then steer itself into a safe orbit. The International Space Station has to dodge tracked space junk roughly once a year, but this method is far from perfect. Below around 1,000 kilometers, Earth's atmosphere is incredibly diffuse, but it's still present. It produces a drag that causes orbits to slowly decay. Now that's ultimately a good thing, as I'll show, but it also means that we can lose track of space junk because the amount of drag can change, in particular during times of high solar activity when more energy is pumped into the atmosphere, causing it to puff up and cause increased drag to higher altitudes. The smaller the space junk, the more susceptible it is to atmospheric drag, and that gives us a sweet spot for lethal debris. Pieces of junk in the size range 1 to 10 centimeters that are the hardest to track and almost impossible to keep track of, and yet are still large enough to cause these lethal collisions. The kind of collisions that can obliterate a satellite if they hit right in the main body. And there are something like 500,000 of these hypervelocity space bullets flitting around out there. Improved tracking facilities can help here. Better, faster observations will help us survive this game of cosmic dodgeball a little longer. But tracking only goes so far. Junk smaller than around a centimeter can't be tracked at all. Your paint flecks and rocket exhaust and shards from prior collisions. The only way this stuff gets cleaned up is if its orbit decays. I already mentioned that orbits decay due to interaction with the upper reaches of Earth's atmosphere. Below around 1,000 kilometers, that drags slow satellites, causing them to fall into lower orbits where the drag is even greater. And this is another type of positive feedback loop. Orbital decay accelerates until the satellite finally burns in a glorious blaze of re-entry. Satellites in low Earth orbit may need to be boosted up to a few times per year to prevent this in-spiral. During a maximum of solar activity when our atmosphere extends further out, the lowest satellites need to be boosted every 2 to 3 weeks. That is annoying, but orbital decay is the most important process for cleaning low Earth orbit of defunct satellites and debris. Ultimately, the Kessler Syndrome can be avoided if orbital decay cleans up low Earth orbit faster than new launches and new collisions fill it. Okay, let's look a bit harder at the sources of space junk to see if these mitigating processes have any hope of saving us. Over 40% of the catalogued space junk is debris from the upper stages of a handful of US rockets that exploded after releasing their payloads. These, plus a few other catastrophic events, are responsible for most of the fragmentary space junk. Notably, we have the 2009 collision between the Iridium-33 communication satellite and Cosmos 2251, a deactivated Soviet military satellite. With a collision velocity of 11.6 kilometers per second, it was less a smash than a splash, creating hundreds of fragments large enough to destroy other satellites and tens of thousands that could damage or deactivate satellites. Relatively few events have produced most of our most dangerous space junk. For example, we have the times that nations deliberately destroyed their own satellites. The US did this in 1985 with an air-to-space missile, and China demonstrated their capability in 2007 with a ground-launched kinetic kill vehicle. The US followed a year later with Operation Burnt Frost, ostensibly to eliminate the risk of re-entry of a tank of toxic hydrazine, and the re-entry of that stuff would have been very bad, but the timing after the Chinese launch does make you wonder. The issue with destroying satellites is that the fragments don't stay in the same orbit as the progenitor satellite. They quickly smear out in a ring around the Earth, making tracking and avoidance that much more difficult. John Gabbard, who was working at NORAD tracking missile test debris in 1960, noticed that debris also spreads out up and down. This increases the altitude range of the risk, and can also mean that collisions in fast-decaying orbits can still generate long-lasting debris. So, bringing this all together, we can paint a picture of our trashed orbital space. Each collision tends to populate a wide swath of low Earth orbit with dangerous debris. That debris then decays in orbit, very slowly for the highest orbits, quite quickly for the lowest. But those lowest orbits are continually repopulated as debris rains down from higher up. For example, even though the International Space Station orbits several hundred kilometers below where the Iridium Cosmos collision happened, on multiple occasions, it's had to perform collision avoidance maneuvers to avoid debris from that collision that's sinking through its orbit. As long as the self-cleaning of the lowest orbits outpaces the introduction of new debris, we avoid exponential buildup. But these lowest orbits are the most useful and cheapest to launch to, and so are the most densely populated. Add to that the rain of debris from above, and these are the most at risk for the Kessler Syndrome. So how long until we get the collision cascade? Well, actually it's already happening. More debris is produced than is removed. Exponential buildup doesn't have to happen over the course of a 90-minute Hollywood movie to be dangerous. In 1978, Donald Kessler estimated that the first satellite collision would probably happen sometime in the next 2 to 3 decades, which was pretty spot on with the Iridium Cosmos destruction just over a decade ago. But the time between subsequent collisions should be shorter, and indeed there have been several now, although thankfully none as cataclysmic as the first. We're currently in the slow part of the exponential rise, so we have years or decades of useful space ahead of us. But that can change if we change our launching habits for the worse. This is where Starlink deserves a mention. SpaceX plans to launch a constellation of over 40,000 satellites as a global internet network. This will increase the number of satellites in orbit by a factor of more than 10. Now, SpaceX insists that they have collision mitigation systems planned, even if they haven't told us exactly what those are. But even your best collision dodger can't do much against an untracked and untrackable shard of debris. One hit can turn your agile debris dodging ninja satellite into just another hunk of debris. I should add that Starlink will be in very low orbit and so has a fast decay time under 5 years. That might be enough to mitigate the dangers in this case, but Starlink isn't going to be the last giant swarm of internet satellites. In fact, it's sure to inspire other companies and nations to launch their own, presumably at some point, some of them without the same care that SpaceX claims to be taking. Okay, let's take the worst case scenario. The Kessler Syndrome accelerates, churning up low Earth orbit into a cloud of shrapnel. What comes next? Some sci-fi writers like to present the Kessler Syndrome as an impassable maelstrom, a giant space blender, effectively imprisoning us on the Earth. That's a bit dramatic. The danger is for objects spending any lengthy period of time in those zones. For a rocket passing straight through on its way to higher orbits or to more distant parts, the risk will probably be tolerably low. Higher orbits, like medium Earth orbit where the GPS satellites live, will probably also be okay due to the relatively low density up there. Still, there are rocket boosters left over from launches to high altitudes. Maybe they could be destroyed in collisions in low Earth orbit, creating a train of debris that wreaks havoc higher up. But the real risk is for anything trying to stay in low Earth orbit. At the late stages of the Kessler Syndrome, the space below a couple of thousand kilometers may be largely unusable, at least for a while. At the very least, the cost of maintaining a satellite presence will be prohibitively expensive, with satellite lifetimes dropping drastically. We'll have to curb our appetite for global digital communication for at least several years while we wait for the junk field to fall back to Earth. After about a decade, very low Earth orbit up to 400 kilometers will become usable again. Or we could start taking more care right now. It's possible to plan to deorbit booster rockets and old satellites or send them into safer graveyard orbits. And all sorts of new technology are being developed to do this stuff, like huge deployable sails which increase drag and cause trash to fall faster, or even electromagnetic tethers which push on Earth's magnetic field to deorbit a satellite. The key will be better organization and cooperation between nations and between companies to maintain our cosmic front yard and to continue our safe use of Earth's orbital spacetime. This show would be much harder to do without the help of the Spacetime community on Patreon. Don't worry, we'll keep doing it no matter what, but I gotta give a huge shout out to the Patreon crew. You guys really help the show to make ends meet. And today's extra special shout out goes to Tiffany Poindexter, who's supporting us at the Big Bang level. Tiffany, we've used your contributions to fund a research program to solve the space junk problem. Our plan is to deorbit all of the smaller pieces of that shiny debris right over your house, where they'll burn up on re-entry in a beautiful fireworks display in celebration of your awesomeness. Obviously we can't do that for the bigger stuff because that'll hit the ground, so please let us know where you'd like us to deorbit all of that. Our last episode was on Planck relics, those subatomic scale black holes that could be literally everywhere and even explain dark matter. Let's see what you guys had to say. Matt Kelly asks what happens to normal matter when it interacts with one of these tiny black holes. Well, first of all, Planck relics would be so impossibly tiny that all matter would be like empty space to them. Give them any velocity at all and they stream right through matter as though it isn't there. The gravitational interaction is weak, except right next to the relic on the scale of the Planck length. If you could somehow get an elementary particle like an electron within that range then perhaps it would be absorbed and the relic would start to grow. The problem then is that the black hole will immediately Hawking radiate back down to a Planck relic. That'll happen long before the next particle is likely to hit, so Planck relics will stay Planck relics unless you can somehow force feed them at an enormous rate. Joanna Mueller never realised that the Planck mass is such a huge thing. I know, right? 0.02 of a milligram is giant compared to the 1.6 by 10 to the minus 35 meters of the Planck length, or the 5 by 10 to the minus 44 seconds of the Planck time. But the Planck mass defines the mass of a black hole 1 Planck length in radius, and remember, black holes are massive. Bleeding Leader Q asks whether a region that is dense with Planck relics would emit high energy radiation as the relics merged and then Hawking radiated again. So this is the sort of extremely cool thought that astrophysicists love because it's something that we can look for. Unfortunately, these suckers are so small that they would never ever merge, even if they got within an atomic nucleus width apart. They just fly by each other. This is what makes them the perfect candidate for WIMPs, the weakly interacting massive objects that may explain dark matter. Several of you hypothesized that the existence of tiny black holes everywhere perfectly explains one of the most vexing paradoxes in the field of domestic mechanics. As in, it explains what happened to your lost socks, or lost screws, or the money in your wallet. It's also a great excuse for why you didn't finish your physics homework on time. No self-respecting physics professor can confidently say that a Planck relic didn't eat your homework. It also explains why I don't have a funnier joke to end this episode. I swear I wrote one down, it just vanished.